This lecture addresses quadratic functions in business. So we just learned the quadratic formula, and while you're watching this lecture, it would be great if you could have the quadratic formula ready on your page so that you're able to use it. And also you're going to want to have your calculator, and then you'll be ready to crunch out these numbers. Because when you're doing business applications, who knows what kind of crazy numbers you'll have to deal with. Okay, so where do quadratic formulas appear inside business? First example, market equilibrium. You guys remember what we talked about when we talked about the theory of supply and demand? That's the way that they price different commodities. So usually when we're talking about pricing a commodity, we will plot the quantity on the x-axis, and we will plot the per item price on the y-axis here. And remember that usually suppliers have a certain way that they act, where if the price is going up, they're going to want to supply more of that thing. As the price goes down, they're not going to like that as much, so they won't supply as many of that thing. And then demanders, so that's the supply. The supply line usually goes up. And then the demanders, that's the other line. Demand line, remember D for down, demand usually goes down, so that's demand. And that's because when the price falls like this, then the demanders will say, oh, that's a really good deal, so I'm going to buy more of that. And then what happens is that those two lines, one going up and one going down, will cross each other at a very special spot, and that special spot locates for us the market equilibrium quantity, the quantity on the x-axis, and the market equilibrium price on the y-axis right here, okay? So before, when you studied the market equilibrium, you saw that both of them were linear, and that eventually made us solve a two-dimensional system of linear equations. This time we're going to move on to say maybe the supply and the demand are quadratic in form. Okay, so let's say, for example, I have two pricing functions. P equals Q squared plus 100, and P equals minus 20Q plus 2500. Okay, so let's look at these for a minute. I didn't write which one is supply and which one is demand, but from the picture there, knowing that one of them is going up and the other is going down, and from what you know about quadratic functions and linear functions, can you pick out which one is supply and which one is demand? Okay, good, that's right. So supply is the one that goes up, and you see the coefficient next to the square there, the A, says that's going to be an up-facing parabola. So this one is going up, so that would be supply. And then the other one, actually the other one is linear in form, and its slope is negative, negative 20, so it's going down. So that's going to be the demand, that one goes down. But again, the question is, where is the market equilibrium located? So basically, we need both of these to be satisfied at the same time. Okay, so please note, these are not both linear. So we cannot use a method, say, of elimination, trying to add or subtract them like we saw for linear systems. We'll have to use another method, and what we want to do here is say, well, if they're both equal to P, and we want them to be equal to each other, then we'll just set both of the right-hand sides equal to each other. And whenever this equality is satisfied, that is going to locate the market equilibrium. Okay, can we use the quadratic formula? I know you really want to. You can't wait to use the quadratic formula, but not yet. Because remember, when you use that, everything has to be on one side and set it equal to 0. Okay, so let's go ahead and put everything on one side. We'll bring this over like this, and then we'll subtract that over, so we have minus 2400. Set it equal to 0. Now's the time where, if you see a quadratic form, you can just try to recognize the A, the B, and the C, and you can go ahead and use that awesome formula you just learned. I know, you can't wait. And then you could crunch it out and get possibly up to 2 real and distinct roots. Okay, so that's one method, and then the other method is factoring. Okay, so if you look at this kind of hard and you say, oh, I see the factors there, then go ahead and try to factor it. 2400. Okay, so 6 times 4 is 24, so 60 times 40, That would work, 60 and 40, because the difference between them is 20. So if you want to think of it that way, then you could say Q plus 60, Q minus 40. If you do go the route of factoring, you want to really stop and make sure that you have the correct factors, which is to say that the product here equals the constant coefficient, and the sum of the two of those things there is going to equal the linear coefficient. Checks out good. So then I know this is the answer for the factoring, and therefore I can say Q is either equal to minus 60 or it's equal to positive 40. Okay, so those would be my 2 points at which this quadratic function right here, if I graphed this function, you would see, if you want to do it, graph this function here to confirm that you have 2 roots, 2 zeros, located at Q equals minus 60, Q equals 40. Can I just answer as both of them? Keep in mind domains and context. That's why we learned that about functions. Where's the domain of this type of function? So the quantity would have to be greater or equal to 0 here. Doesn't make sense to have a negative quantity. So I'm going with a quantity of 40. So going back to this graph here. Now for this problem, actually, I'll just make it a little more accurate. In this problem, our orange demand line actually is just linear. So that's what it looks like. Okay, but we solved it out, and make sure you got your variables straight. We solved it out for Q. So Q is the quantity, so that tells us that our market equilibrium quantity is going to settle at 40, and then our price is going to settle at, I don't see it on there. Where am I getting my price? That's right, you have to plug it in, and you can plug it into either one of these equations. Once you get Q equals 40 right here, I could just use the top one. P is equal to 40 squared plus 100, and so that's going to be 1,700. Ooh, that's a pretty penny right there. So the market would like to demand 40 and supply 40 of these, and the per item price is $1,700. So it must be something pretty fancy. And there you go. Same thing you saw before. It's just the new stuff is that if you have any quadratic terms inside either one of these functions, then you'll have to go ahead and use a quadratic formula in order to obtain the market equilibrium. Okay, so that was a quick example of where quadratics can show up in business, but it's more likely that you would probably encounter a quadratic form, let's say, inside your revenue function. So let me show you where a quadratic form can come from when you're trying to form your revenue. And actually, this still has to do with the philosophy of demand, the fact that the market will demand more items if the price of the item is lower. So I'm going to put this under bulk pricing. So example and revenue. Let's say that we have some sort of bulk pricing, and I wonder if you've ever encountered this in a business. If you buy one, it's a certain price, but if you buy more, then the price starts to go down. The per item price will go down to try to encourage you to buy more. Okay, so that's kind of linked to the theory of demand there. Let's say that an item costs, its original price is $45.50. For each one of those, okay? But then the store wants to give you a deal. I know that price is kind of high. So for every additional item you buy, more than one, I will take off 50 cents of the per item price, okay? So for each additional item purchased, then the per item price for all the items drops by 50 cents. Does that make you want to buy more? I hope so, because that's my whole point, is I'm trying to sell more of them to you. So I've actually made the price of my item, the per item cost, a function of how many items you're going to buy. Okay, so here let's let X equal number of items purchased. And let's let P of X, now a function dependent on X, be the per item price. And let's see if we can develop a mathematical model for a statement for the P of X. And then don't forget that our revenue is always formed by saying the per item price multiplied by the number of items. And you can see the number of items purchased is X. So to put this in terms of our setup here for our word problem, the revenue will be formed by taking the price function, multiplying that by the number of items purchased. P of X times X. In the past, you may have seen revenue modeled with P times X, where P was a constant price. And that's one way to do it, but here we're going to show you how the quadratic formula pops out. First question, what type of function do you think we will use for P of X? A linear function, yeah, it goes down by a constant amount each time. Each additional item purchased leads to a 50-cent discount per item. So that means we're going to use a linear function where the price is dropping by 50 cents each time. Okay, so sometimes it might be easier for me to maybe just picture the price function as I'm attempting to form a mathematical equation for it. Okay, if I buy one item, if X is equal to 1, then what's the price? $45.50. That's right. So 1 point on this line is 1, $45.50. Okay? Now if I buy 2 items, what's the per item price? $45. It went down by 50 cents. So I'm going to put the 2 all the way over here. Our next dot on this line would be 2, $45. Okay, and so you can see that since it's constantly going down by 50 cents for each item purchased, here keep in mind that this isn't centered at 0 by the scale of things, okay, but it's going down like that, so I'm going to want to use y equals mx plus b type of form. You could get the m by doing the lines here, by doing the point slope thing, but actually, do you guys know what the m is already? M equals, can you take a guess what I will just write for M? Negative 50 cents, right? Because going down by 50 cents each, so just by understanding the problem, the M is going to be equal to negative 0.5. Okay, and then what do you think the y-intercept for this is going to be? Keep in mind that conceptually the y-intercept is the value of y when x is equal to 0. Not 1, but 0. So if you go backwards a little bit by 1 unit, the y-intercept is going to be at 46. That's right, I went backwards, so I added 50 cents. So you can confirm that if you want by using these points to form the line, but also just by thinking of the context of the problem, m is negative 0.5, b is equal to 46, so my price function p of x is going to be 46 minus 0.5 times x. And I'll just check that in my head before I move on, because when you got a multi-step problem like this, you want to make sure that every step's right before you move on. Otherwise, your mistakes will propagate through the whole problem, and you'll have to do everything again. So let's just make sure. When x is equal to 1 item, what's the price? 46 minus 0.5, $45.50. If x was 2, that would be 46 minus 1, so it would be $45. It makes sense. I'm doing it right so far. Okay, so here's our price function, and then let's just write down what our revenue function is going to be. It's going to be price times number of items, and the price depends on the number of items, which is the new thing. Then we're going to multiply that by x, and so now I'm going to FOIL that through, or actually just factor it. So you got 46x minus 0.5x squared. Nice. That's our revenue function now, okay? What type of function is it? Quadratic function. Alright, so if it's a quadratic function, let's see if we could recognize what's the a, b, and c, just in case we need to use them. Why don't you go ahead and write down on your page, what's the a, b, and c? Okay, the a, now watch out because this is out of order. The a always gets multiplied by the x squared term. Even though this is out of order here, I have to keep that in mind. So the a is minus 0.5. The b goes by the linear term here, that's 46. And what's the c? I don't see the c, but it doesn't mean it doesn't exist. The c, actually it's hidden there, is 0. It's just adding 0. Okay, so you still have the a, b, c there, and maybe we will have to use them. Alright, so let's move on in this type of problem. I wonder what kind of stuff I would be interested in here. I would probably be interested in a couple things. For one thing, when would I not make any money? Okay, so we know that we're not going to make any money if we don't sell anything. So one place we're not going to make any money is x is equal to 0. First I'll try to answer the question, when will my revenue be equal to 0? Okay, x equals 0, that's the obvious point, and you can see that if x equals 0 here, sure enough, I won't make any money. That makes sense. The revenue function always goes through the point 0, 0, because if you don't sell anything, you're not going to make any money. However, one thing that you may not have kept in mind is that eventually, if you're offering this price scheme where you're going down by 50 cents each and every time, eventually there's going to be a number of items where the price, according to this model, will be 0. Okay, eventually I'm going to be giving these things away for free, and I definitely don't want to do that either. So what is the other place, number of items, such that my revenue will be 0? So for that, you can use the quadratic formula. If you want to use the quadratic formula, you can to get the roots. Remember, the roots are the places where it equals 0. Or you can still use the concept of factoring. So you've got it in its factored form, actually. Before I unfactored it, we'll go back to its factored form here, and you can see one of the roots is x equals 0, and the other root here will be given to us when 46 minus 0.5x, when that's equal to 0. Okay, so what's that other root? I think I've got it on here somewhere. Oh, maybe I didn't. Good thing I brought my calculator. Guys, solve this one out. At what value of x am I now giving away my items for free because of my cool pricing scheme? 92 items, okay? So if you solve this one out, you get x is equal to 92. So you don't want to offer this deal for a very large number of items. Probably after a while, you're really going to be not making as much revenue as you should be making. So you got to watch out for these points. These are the number of items such that you would make 0 revenue. Another thing I would be interested in is when am I going to get the most revenue? Okay, so there's my revenue function right there. I still have it over there. And if I want to know the most about any function that I'm working with, the best bet is going to be to graph the function. That's why you get your graphing calculators with you. So go ahead and practice. Here's the function right here. You can type it in like this or in the other factored form. You type this equation into the y equals and obtain a graph of it so we can think about all values of x and what kind of revenue we would be making at each and every value of x. Okay, go ahead and graph that. If you're taking a test, it's really nice to have a picture while you work through your math so you don't have to double think yourself or question your answers. Okay, and one thing that I already found out is that when x is equal to 0 and when x is equal to 92, those are both the points where I'm not going to make any revenue. Okay? In between those points, you can see everywhere that r of x is greater than 0. I'd like you to observe that this is indeed a down-facing parabola because the a is negative. Okay, where's my favorite point on this graph? Right between the two roots, exactly middle point, right between the two roots. And this right here is going to be the vertex. And remember that when you have a down-facing parabola, the vertex represents the maximum point on the parabola. And this is where my revenue is going to be highest. So that's probably the number of items that I would really try to convince people to buy, you know, if I wanted to maximize my revenue. And once again, for each and every parabola, if you have the two zeros, the vertex is always located right between them. So if you want, you can take the average of the two zeros, you add them together and divide by 2, and then you'll get the midpoint. But the other way to get the midpoint, remember, is the vertex formula, which is x is equal to minus b over 2a. And so from what we discussed before, over here I'll rewrite it. The a was equal to negative 0.5 and the b was equal to 46. Okay, so the vertex is located at negative 46 divided by 2 times negative 0.5, and that's negative 46 over minus 1, and that's 46. So there's two ways for you to figure out the vertex. One way is the vertex formula. The other way, you'd only want to use it if you already computed the roots. But if you do have the roots, then it's just the average of the two roots. So 46 items is the number of items at which my maximum revenue will be obtained. But what is my maximum revenue? What is the maximum revenue possible? Okay, do you remember how to get that? Pause the video, see if you can get that answer. That's right, that comes from plugging in x equals 46 into your equation. So we'll have to do that r of 46 is the y value at which our revenue is maximized. So that's going to be 46 minus 0.5 times the x value of 46 times the 46. Okay, and then I already worked that one out. I got 1050. 1058, $1,058. So our vertex, if we wanted to write it as a point, would be 46, 1058. Okay, I'll just not have that there so it doesn't confuse. Okay, so if we sell 46 items, we will obtain the maximum possible revenue off one sale of $1,058. Which is to say, is that what I should recommend to my boss that we advertise, buy 46, it's a great amount to have? No, not necessarily. So the next thing I want to show you guys is that when you're thinking about your business, not only would you like to analyze your revenue, but actually more so, you want to analyze your profit. Because what's happening to your cost? Is your cost fixed? Is it growing linearly? Maybe your cost is even growing quadratically. And your profit is really what you're after, the difference between your revenue and your cost. So now let's do another one where we're not just going to look at the revenue, but we're going to look at actually both the revenue and the cost, and we're going to see how to maximize profit, okay? So that's what we really want to get max profit, not just max revenue. Keep in mind the difference, max profit. So for this new example, let's say I'm given two functions, a cost function of 24,000 plus 45x plus 0.1x squared, and a revenue function here, 425x minus 0.9x squared. Okay, let's just look at these for a minute and talk about what we've already seen and learned. Revenue, this is a familiar form just from the last example, that the reason the revenue is like this is because there must have been some sort of pricing, some sort of discount pricing going on. Okay, so if we look at it in its factored form like this, remember that revenue is always equal to number of items times price per item, which sometimes itself can be a function of x. And here, maybe the original price for one item would be $4.25 minus 0.9, but then it also goes down by 90 cents for each additional item that you buy. Okay, so that's where we could get something like this. And then the cost function here, we won't really go into how to derive this, but we can just talk about where to find the fixed costs and where the variable costs. So we've seen that before in linear models. One thing that's the same is that your fixed cost in your cost function is still the part that does not multiply the x. Okay, so my fixed cost here is 24,000. That's a lot of fixed costs, but who knows, maybe I'm making something really cool. And then my variable cost, I just want to show you that this is different than linear functions. In a linear function like this, your variable cost would just be the linear term. But now, with the addition of a quadratic term, this entire x-dependent cost is my variable cost, okay? So keep in mind that your variable cost now includes a quadratic term, and if you want to consider the marginal quantities, you can no longer just take the $45 as your conceptual marginal quantity. You'd have to actually do a little bit more work, and computing marginal quantities will become easier as we get into the theory of calculus. Okay, so I won't go into that right now. But just watch out and don't get misled to think that your marginal quantity is still the coefficient of the linear term, because it is not. Your variable cost is now quadratic. So many equations, right? Why don't we just take a minute to plot them, okay? If you have one of those really nice graphing calculators, then you're in luck, because when you plot two different things, you get those lines in different colors. But even if you don't have that to your advantage, you can still tell the difference of which one's going to be your revenue and which one your costs, because typically, actually always, your revenue goes through 0, 0. Your cost usually does not go through 0, 0 because you have some sort of fixed cost, okay? So that means that if I gave you these two things, like let's say I gave you this, and then maybe I plotted this one like this. Okay, so which is which? Which one's the cost? Which one's the revenue? Yeah, from what I just said, you see the cost function will not go through 0, 0. Due to the fixed cost, this cost function does not go through 0, 0. But if you don't sell anything, you don't make anything. So the revenue always goes through 0, 0, and that's how you can tell the difference. Okay, so most businesses want to know, where's my max profit? But where even is my profit on this graph? Where do I even see my profit? Do you guys know where the profit is located? I didn't graph the profit. I could take the difference between these equations, get a new equation for profit and graph it. But even just with these equations, I can start to visualize profit, because profit is the difference between revenue minus cost. Okay? So that, graphically, would be the difference between the red line and the green line. When the red line is greater than the green line, the revenue is greater than the cost. And so here's a region of sweet, sweet, positive profit. Okay? That's the region I'm interested right there. What about the intersection points? What are those intersection points representing? The one that's right here and one that's right here. Are these cool spots to be at? Do you like these spots? Break-even spots. That's right. These are the places where P is equal to 0. And so I'm breaking even right here, and I'm breaking even right here, and that is profit is equal to 0. Okay? So when these things intersect, they're equal, so the P would equal 0 there. And then when the green line is greater than the red line, that's when my cost exceeds my revenue. So my profit is negative. So I'm probably going to want to avoid the places where I'm outside the break-even region and my profit is negative. And then between the break-even regions right there, that's where my positive profit is. But I want to maximize my profit, right? So where's my maximum profit? It's going to be graphically on this graph. Your max profit will be wherever the difference gets its widest, okay? So it looks like over here, just a little bit of profit. Then my profit increases. There's some big, nice profits right here. Over here, not so much profit. My max profit is hiding in here somewhere, but I want to figure out what that is, okay? So actually, why don't I go ahead and just write down profit as the difference between revenue and cost, and then I'll be able to graph that, and then we can compare that graph with the graph we see here. Okay, be really careful when you're forming the profit function. You're going to copy down the revenue function, and then you're going to put a minus and a big parentheses. That's the thing that people forget, and it really gets them in trouble. So open the parentheses, and then you copy down the entire cost function like this. And then you close that big parentheses. That way you're guaranteed to be factoring the minus sign through to each one of those terms. And then what happens when you combine these terms? Pause the video. Do this yourself. Make sure you know how to do this. Okay? And then once you combine the terms, what I got and what you should get is minus x squared plus 380x minus 24,000. Okay, now you might have these terms jumbled up, like maybe you have this one in the front or you have this one in the front. It doesn't matter if the terms are out of order. You just have to keep in mind where is the A, B, C located. Okay, because if you're going to apply the quadratic formula in order to find the roots of profit, which would represent the break-even points where the profit is 0, then you're going to have to correctly identify A, B, and C, and those have to do with what type of term, quadratic, linear, or constant, you are multiplying by, not so much the actual order of the terms. Okay? So now we have our ABC, and if we wanted to, we could take the ABC, and you guys have the quadratic formula handy somewhere? You have your calculator handy somewhere? Okay, take the ABC, plug it into the quadratic formula, and then you should be able to locate the x values at which the break-even points occur. Okay, did I do that? Did I do that? Yeah, I did do that. Did you do that? You want to get a lot of practice, okay? Before you have to encounter problems like this in, let's say, a timed proctored exam or something, you want to make sure that you've practiced plenty of times. Alright, so let's see what I got here. I got 80 as the low one, and I got 300 as the high one, and I hope that you guys are actually practicing and obtaining those numbers using the quadratic formula. Okay, so those are the two roots of my p of x, which is to say, this is a location where p of x equals 0, this is a location where p of x equals 0. Oh, why don't I just draw a plot of p of x so we can compare it with that plot there, and then we can really see, visualize, where we will find our max profit, okay? So this is the same problem, same x, but instead of the r and the c, I'm going to draw the p of x. And I know the p of x actually goes through 0 when x equals 80 and when x equals 300, so this is what my p of x looks like. Notice that it's a down-facing parabola because the a is less than 0. So it's down-facing, so just like we confirmed with the other graph, this is a place where p is greater than 0. Over here, less than 0. Too many, also less than 0. Kind of counterintuitive. That's why you really want to keep in mind that making more things is not always necessarily better if you've applied some sort of bulk pricing, or if your costs are increasing at an unusually large rate when you have to make a lot of them. Okay, so I definitely want to keep my number of items in production and sales between 80 and 300, but where is my favorite place to be? How do I use math to find the favorite place? First of all, did you guys see what I'm talking about here? The favorite place, meaning maximum profit, is located at the vertex right here. The vertex of a down-facing parabola represents the max value. Okay? And what x value is that going to be located at? Well, we could use the vertex formula, x equals minus b over 2a. And there's the a, b, and c right there to help you. Or, if you like, you could do the other one where you take the average of the two roots, because you know the vertex is right in the middle of the two roots. A parabola is symmetric about its vertex, so you can average the two roots. So I'll take this alternative method, but I would encourage you to also apply this formula just so you make sure that it checks out. The average of the two roots, 80 and 300, would be 80 plus 300, and then divide that by 2, and then what you're going to get there is 190. Okay? So you can either do it that way, or x is equal to minus b over 2a, and so that's also 190. So double checking is always great. Check your work. The x value for the vertex is located at 190 items. Okay, so how much money can I really make? What is the maximum profit that I can actually hope to make? Keep in mind that you have to take the x equals 190 and plug it back into this formula. Okay, so vertex at x equals 190, and then p of 190, you have to calculate that. So negative the quantity 190 squared plus 380 times quantity 190 minus 24,000, and that seems like a lot, but I guess when you square 190, that's even more, because that turns out to be 12,100. Okay, so $12,100 is my maximum possible profit, which is to say that this vertex is located at 190, comma, 12,100. Okay, so there you have it. That's where my maximum profit is located. And if we go back a little bit, I just want to show you how this is different than maximizing your revenue. Okay, so let's just go back a little bit and see that the max profit, we did all that work to find that 190 is our sweet spot there. Where is the maximum revenue located? What if I asked you to find the maximum revenue? Why don't you pause and try to do that separate problem, locate the maximum revenue. Okay, so max revenue, that's going to be at the vertex of the revenue formula, okay? So here's the revenue portion of the formula, that was this part right here. So if I let x equal minus b over 2a there, then I'm going to get, let's see, minus 425 over 2 times minus 0.9. And that's equal to approximately, that one didn't come out as a perfect whole number, but it's around 236.11. Okay, so my maximum revenue, when my revenue function would be highest, would be 236.11. This is the maximization of R of X. But from the further analysis of the profit, we can see that actually producing and selling less items at a point of x equals 190 is actually a better spot for us to be in than maximizing our revenue, because since our cost function is also increasing at the same time, this width is actually smaller than this width right here at 190. Okay, so always keep in mind that you want to usually go after maximum profit, not so much just the revenue.